So let's briefly go back through our process of fatty acid synthesis, starting with a high level of glucose. Glucose will enter into the liver. It will generate our pyruvate. Pyruvate is converted to acetyl-CoA, which condenses with oxaloacetate to form citrate. Citrate is shuttled out of the mitochondria and cleaved by citrate lyase into oxaloacetate and acetyl-CoA. Acetyl-CoA, via our regulatory enzyme, acetyl-CoA carboxylase, is converted into malonyl-CoA. Malonyl-CoA and acetyl-CoA are used in fatty acid synthesis to generate palmitate. Palmitate is used to synthesize triacylglycerols. We'll look at this process on the next slide, but essentially each fatty acid chain is activated by the addition of a CoA group to generate a fatty acyl-CoA and is added to our 3-carbon glycerol 3-phosphate molecule. The addition of 3 chains generates our triacylglycerol, which is packaged in VLDL particles, which are released from the liver and will enter circulation to deliver our triglycerides to the adipose for storage. So our newly synthesized fatty acids in the liver need to be transported to the adipose where they're stored in adipocytes. The storage is in the form of triacylglycerol. The synthesis of triacylglycerols from free fatty acids in the liver and the adipose is similar. The difference here is the generation of glycerol 3-phosphate. In the liver, glycerol 3-phosphate can come from either the phosphorylation of glycerol via glycerol 3 kinase, or it can come from glycolysis. Adipose lacks the glycerol kinase, and the glycerol 3-phosphate comes exclusively from glycolysis in the adipose. In both tissues, triglycerols are produced in which the glycerol 3-phosphate reacts with fatty acyl-CoAs to form phosphatidic acid. And then dephosphorylation generates our diacylglycerol. The addition of another fatty acyl-CoA will generate our triacylglycerol. In the liver, the triacylglycerols are packaged in VLDLs, which can be sent out in circulation, whereas in the adipose, the triacylglycerols are directly stored. Remember, these molecules are lipid-soluble and require carriers in the bloodstream. The synthesis of VLDL particles is similar to the synthesis of chylomicrons. So the synthesis of our VLDL particles takes place in the liver. And it starts with the synthesis of our apoprotein, ApoB100 in this case, in the rough endoplasmic reticulum. It's then packaged with the newly synthesized triacylglycerols in the ER and the Golgi to form our VLDL particles that are excreted from the cell. These VLDL particles have a different lipid composition when you compare them to chylomicrons. So our total triacylglycerol in a VLDL particle is less than a chylomicron. and our protein contribution is elevated, as well as our cholesterol. So VLDLs are synthesized in the liver and contain both newly synthesized triacylglycerol as well as cholesterol. Cholesterol can also be esterified to be cholesterol ester. And these are all, again, surrounded by a phospholipid monolayer. VLDL particles are smaller than chylomicrons. Once outside of the liver, our VLDL particle, full of triacylglycerols, interacts with lipoprotein lipase via the interaction of ApoC2 and lipoprotein lipase to hydrolyze triacylglycerols into free fatty acids and glycerol. The fatty acids will then move into both the muscle and the adipose, and in the muscle they'll be oxidized, whereas in the adipose they're recombined to form triacylglycerols. The glycerol released in the hydrolysis of triacylglycerol will be recirculated back to the liver. So similar to chylomicrons, once in the blood, these VLDL particles will interact with lipoprotein lipase via the activation of ApoC2. Lipoprotein lipase will hydrolyze the triacylglycerols into both free fatty acids and glycerol, and the fatty acids can be stored in the adipose. These fatty acids, again, are activated to a fatty acyl-CoA and used to synthesize triacylglycerols in the adipose. Under high insulin levels, or in the fed state, when glucose is high, glucose uptake by the adipose cell will also be increased, and that will increase our necessary 3-carbon glycerol backbone. Likewise, insulin will stimulate lipoprotein lipase. Once the VLDL has interacted with a lipoprotein lipase and triglycerides are removed from the particle for the most part, the VLDL becomes an intermediate molecule, or IDL, and will eventually mature to an LDL, or low-density lipoprotein. We'll look at the fate of low-density lipoproteins in the next module when we look at cholesterol synthesis. Keep in mind that these particles retain the ApoB100 protein, and that's integral for its function. So more recently, adipose has been shown to function as an endocrine organ, where adipose releases signals that then impact how you utilize fuels. So adipose consists of cells referred to as adipocytes, and the adipocytes are the cells that store our triacylglycerol. So these cells can become bigger as more triacylglycerol is stored, and they can decrease in size as that triacylglycerol decreases. So the two hormones that your text highlights are leptin and adiponectin. Leptin is released from the adipose as triglyceride content increases. It circulates to the hypothalamus via the bloodstream and signals through a JAK-STAT receptor. This signaling signals a cessation of eating, so this is your sensation of fullness. So in the case of obesity, leptin insensitivity has been shown to contribute to this disease. In that case, a leptin is still released, but it isn't recognized, so the signaling cascade is not recognized by the cell, such that the feeling of cessation isn't instigated. In the case of adiponectin, it functions slightly differently. It's released from the adipose and activates an AMP kinase in skeletal muscle and liver. The activation of the AMP kinase increases fatty acid beta oxidation. If you remember from fatty acid synthesis, activation of AMP kinase inhibits fatty acid synthesis and at the same time increases fatty acid beta oxidation. The release of adiponectin decreases as the adipocyte gets larger. And this can have clinical consequences, again, for the obese individual. In the case of obese individuals that have very large adipocytes, this decreases the release of adiponectin. The reduced levels of adiponectin leads to a decrease in the oxidation of fatty acids. And these free fatty acids will contribute to elevated free fatty acids in the bloodstream of obese individuals. We'll look more closely at the hormonal regulation of metabolism in a later module, but you should be aware of these two hormones being released from the adipose. So before we move to fatty acid beta oxidation, let's look at this question. When the liver converts excess glucose into fatty acids, when insulin is high, in other words, all of the following are true except. Let's start at the bottom. So cytosolic acetyl-CoA is converted to palmitate, and the oxaloacetate is converted to pyruvate. This is true. Remember, citrate is being shuttled out of the mitochondria, cleaved via citrate lyase into acetyl-CoA and oxaloacetate. The acetyl-CoA is used to generate malonyl-CoA, and both are used in the synthesis of palmitate. And the oxaloacetate is converted back to pyruvate via malic enzyme. And this reaction generates NADPH. What about D? VLDL particles are synthesized in the liver. This is also true. Our VLDL particles are being synthesized in the liver, and the primary component are our triacylglycerols that are also being synthesized in the liver from our newly synthesized free fatty acids. What about C? Acetyl-CoA and oxaloacetate form citrate that leaves the mitochondria. Again, this is also true. Under high levels of glucose, glucose is oxidized to pyruvate, and pyruvate is converted to acetyl-CoA via pyruvate dehydrogenase. This leads us to B. Pyruvate dehydrogenase is dephosphorylated. This is also true. Under high levels of insulin, pyruvate dehydrogenase is dephosphorylated and active, leaving us with A. Lipoprotein lipase activity is low. This is incorrect. Lipoprotein lipase, under levels of high glucose and insulin, would have high activity. This is an incorrect statement.